This is EE370, lecture 15. So I'd like to quickly revisit one of the questions part of the quiz that I published on Academy. So you had two flops. Some input was being fed in here. And the critical part for this question was the fact that there was a buffer in the clock path. Right? And the question was, if you changed this buffer delay, how does it affect the hold slack? So let me generalize. Let's look at, if you change this buffer delay, how does it affect either the hold or the setup slack? Right? So in this particular question, anytime you see a timing analysis question, you have to identify the path in which you are doing the analysis. So you have to identify the launch flop and the capture flop, right? Or something that is being launched and something that is being captured. And the setup and the hold constraints are now associated with the capture flop. You are checking if the data is getting captured correctly. So here, who is the launch flop? Who is launching the data? A is launching the data, B is capturing the data, right? So this is your path of analysis, right? So actually, you have to consider, when you're doing an analysis in a path, you have to consider signals propagating in two different paths. One is how is the data propagating to the D pin. The other is how the clock is propagating, right? Now, if you had a delay here, then this had to be taken into consideration when you do STA. Now, in this particular case, the clock is reaching both the launch and the capture flop at the same time. So, do you think this buffer delay is going to cause any difference? No, right? Whether you increase it or decrease it, it has no bearing on the timing analysis to be done in this path. Now, however, if I had asked you, so now your DA is an input, right? Now, if I ask you, what should be the time before the clock edge that DA should be stable? What should be the time after the clock edge that DA should be stable? So, in effect, if this is your clock edge, we now understand that the input here has to be stable for some time around this clock edge. Right? Now, if I had asked you that question, then your launch is happening outside your system. That is basically you're figuring out at what point this DA has to remain stable so that this particular value is getting captured in the capture flop A. Right? So if I ask you the question as to how much before the clock edge should DA be correctly set up, then you will have to analyze the timing with A being the capture flop. And if A is a capture flop and you have to report numbers with respect to this clock signal, then you are looking at analysis in these two parts. Right? So the launch is happening outside your system and you have to figure out by what time that has to be launched correctly and held as a constant value. Right? So in that analysis, this buffer delay would have played a role. But if you're only given a circuit like this and you're asked to look at setup and hold slack, if nothing is mentioned about the inputs, it is assumed that the inputs are held steady for correct capturing. And then the only path to be analyzed is from getting launched from A to getting captured from B. So only the clock delay in that path will matter. And this buffer delay was not affecting that, so it had no bearing on your setup or hold slack for this. Is that okay? Okay, so then we move on to the next topic. So today, first we are going to understand a read-only memory. Or a ROM circuit. Right? So the moment I say read-only memory, what do you understand? Are there questions on STA? Okay, so read-only memory. What do you understand? There is some memory element. This has some data inside, right? So this will have multiple locations in which you can save data. I'm going to assume that it has 4 locations starting from 0, 1, 2, 3. And in each location, let's say we have a 4-bit data. So let's say this is, let's say we have a 4-bit data. So let's say this is 0010, this is maybe 1010, 1001, and 1111. The fact that it is read only means that you cannot write data into it, at least not in a regular manner, right? So therefore, what do you think should be the input to this? So this is a memory block. I have stored some information inside it, right? What do you think should be the input? Address, right? So if you want to read out the data in a particular position, you will have to give the address from which you want the data to be read out. So in this particular case, if I tell you that there are 4 positions possible inside, how many number of bits should you use for address? 2 bits, right? You want to choose between 0, 1, 2, 3, and this information can be presented in 2 bits. So what you have is this. I'm going to call this as address of 1 and address of 0. Right? And what will be the output? What will be the output? You are going to read out the contents in that position. And because you have a 4-bit information in each position, you will have 4-bit output. I'll call this as O3, O2, O1, and O0. Right? So in particular, we say that at every address location, you have a word being stored. So a collection of bits is called as a word. And this particular memory that I have sketched has how many words? It has 4 words where each word had 4 bits. Right? So we say that this is a ROM that has 2 power 2 locations and it has a 4-bit output. So you can represent this as 2 power 2 cross 4 ROM. So in general, if you take a ROM, it can have a k-bit address, and let's say the output is n-bit output. Then it means that you have 2 power k memory locations, which means you have 2 power k words stored in your memory, and each word is n-bit wide. So this is 2 power k into n ROM. Okay. Now, because it is a read-only memory, one of the general requirements is that even if this is also a non-volatile memory typically. What it means is that even if you turn off your hardware and turn it on, this information is not lost, right? Now you can construct this read-only memory based on the circuit elements that you already know. So can you give it maybe 30 seconds and see if you are able to come up with a ROM architecture? What is the first circuit element that you are thinking of when I tell you memory? A flip-flop, right? But if I turn on the power to the flip-flop, the data is lost, right? So something else. And you already know all of these circuit elements. You can simply put it together and get a read-only memory. Feel free to discuss for a minute and see if you are able to come up with it. So let me show you the circuit. You can construct a read-only memory by using a decoder and by using OR gates. Right? So quickly remind me, what is a decoder? So I have sketched a 2 cross 4 decoder, which means you can have 2 inputs and you will have 4 outputs. Now in a decoder circuit, at a time, only one of the 4 outputs will become 1, And which of those line is becoming 1 is determined by the value represented in I1 and I0. So if this is 0, then O0 becomes 1. This is 1, O1 becomes 1. For 2, O2 becomes 1, etc. Right? So what it means is that at any given time instant, depending on the values of A0 to A4, you will have only one of the lines going high. Okay. Now, before I start explaining the functioning of this ROM, can you tell me how many words can be stored here? So, this is a read-only memory. How many address bits are being given? 5. Right? Which means you can store 2 power 5 words, 32 words in the system. And what is the length of each word? 4. Right? So this is a 2 power 5 cross 4. It is 4 words because your output, 4 bits at the output, because you can see that O3 to O0 are coming out. Right? Okay, so like I said, you will have only one of these wires going high at a time, and then you have this gigantic 32-bit OR that is ORing all of these. Right? So in particular, this connection, for now just understand that it is going to be programmable, wherein if I put a cross, then it is shorted. If I leave it without a cross, then it is simply not connected. It's just 2 wires passing by, they are not shorted. So let's say I do something like this. And for now, you can assume that for all of these portions, there are no crosses at all. Now, can you tell me the output when A4, A3, A2, A1, A0? Let's assume that this is 0. Can you tell me what is the output for O3, O2, O1, O0? When all of this is 0, the only line that is going high is this. Right? Which of these are going to become 1? All the other lines are 0. Right? When input address is 0, only this decoder output is becoming 1. Now, if the decoder output corresponding to this line is 1, what is the value for O3? 1, because it is shorted. Right? What is O2? 0. What is O1? 1. What is O0? 0. Right? So you will have 1, 0, 1, 0. Is it okay? Quickly tell me what you get if I give 0, 0, 0, 0, 1. From the back section, what value do you get? All zeros, right? Because this line has become 1, but it is not connected to any of the OR gates. Right? Therefore, this is going to be 0. Okay. Now, let's say I power off the circuit and power it on again. Because these connections are hardwired, the connections are not going to change just because you cut the supply to the system. So, when you power it on again, the same information is still retained in the memory. Right? So, yeah, we have constructed a read-only memory using a simple decoder block and an OR gate. So, how many inputs do you think this OR gate has in this given figure? How many inputs does it have? What is the maximum number of inputs that O3 OR can have? 32, right? So now if I make the address bits to, let's say, 6-bit, then you might possibly have to design a 64-bit input OR gate, right? So can you imagine the size of such OR gates? Now let me show you how this gigantic OR gate is going to be implemented. To understand this, let me first take a very simple resistor divider circuit. So I have this very large resistor connected between the output and the ground, and then I have a switch that is connected between some input and the output. Now this path can possibly have some small resistance. Ideal case, the resistance is 0, but otherwise it could have some small value of resistance, right? So I have indicated that as R small. Now when input A is equal to 1, can you tell me what is the output? So input A is 1 and this switch is now closed, which means this is now shorted. What would be the output? So when I say input A equal to 1, if it is easier for you, you can imagine this as being equal to supply. Then what would be the output? Why do you say it is 1? This is a resistor division, right? So this will become equal to VDD into R large divided by R large plus R small. Is there an approximation that you can make here? So if R large is much greater than R small, this is almost equal to VDD, which means your output is equal to logic 1. Okay. Now, what if your input A was equal to 0? What is your output? A is 0, right? This is equal to 0, right? It is logic 0. Now let us consider what happens if the switch was open, right? When A equal to 1, what is the result? Out is equal to 0. A equal to 0, what is the result? Out equal to 0. The value of the A appearing here does not matter because you have this resistance that is pulling down this node and there is no path to pull this up to VDD. This is broken. Right? Is this okay? Then I'm going to make this slightly complicated. Instead of one input, I have connected 3 inputs. Right? And we can go through the same logic again. If all of them are shorted, that is, all of these are connected like this, when A, B and C are 1, what is the output? A, B and C are 1, the output is 1. Let's say A is 1 and B and C are 0. Then what would be the output? Then also the output is 1. Right? So now, if I give you a circuit like this, where I have not connected this portion, right? Then what is the output equal to? Can I write this as A plus C? Right? That's all. So I can construct an OR gate by having some sort of a connection like this. Right? So in effect, this OR gate can be thought of as you have some very large resistance connected to ground, right? And depending on which of these paths are shorted, you will have an OR operation directly happening on this net, right? So this model where you have shown a single OR gate here with a line like this will eventually get implemented by a line with some resistor connections in between these. So the decoder output has to be connected to this line using some switch, and you need to have a pull down path that is able to bring it down if nothing is connected to this line. That's all. Is the idea roughly clear? So as a representation, I will still use an OR gate here, but the actual implementation is going to be some sort of a wired OR. Alright. So now that I have a connection like this, the critical point now is to decide on how I would make this interconnect, right? And depending on that, you have several types of read-only memories available. So one way in which how you make this connection is to use a masked ROM, in which case you would make those connections hardwired during the fabrication. So when you send your design for the fabrication, then only you will tell the foundry for these locations, please make a hardwired connection, right? And immediately after the fabrication, your read-only memory is ready with the type of data that you wanted to be stored forever. Now this makes sense because a fabrication cycle is involved. This makes sense only if you know that you will need that particular data set stored for a very long time and for a large number of devices, because it's going to be expensive. And if you decide to change the data set at a later point, it's another full cycle of design and fabrication. Right? So this has limited usages and makes sense only if you want it over a large number of devices and that data set is going to be constant. Another way is to use a programmable read-only memory, in short called as ROM. So in a programmable read-only memory, when they fabricate it, they will have all of these interconnects made. Right? And you can think of these connections as being made using some sort of a fuse. And to understand fuse, right now think of that as a very thick metal line. Right? So all of these points have been connected through fuses. So you get it in your hand afterwards. So after it is fabricated, you will take it and then you will pump large amounts of current through the fuses that you don't want. So you pump large amounts of current, the fuse gets burned away, it gets blown away, and that connection is now broken. Right? So this way, you get a read-only memory where all the inputs are one, where all the data set is one, and then you blow away the fuses at specific locations so that you get the data set that you want. Now this process of pumping in large currents through certain pins and blowing away the fuse, it's not something that a customer can typically do in the field. You need specific equipment and this process has to be done in a lab. Now the third method is to have a different type of switch called as a floating inverter based gate. Now in these gates, you can program it and erase it. So this is a erasable programmable read-only memory. So just to recap, here the data set is determined at the time of fabrication. It can be done only once. Here the data set is determined after the fabrication process. You can put in the data set only once, because once the fuse is blown away, there is no way for you to get it back. Right? So once you make a zero at some location, it becomes a zero. Now the next portion is where you have the option to erase it and then write the data back. So in these cases, you would use a specific type of switch where the switch can be turned off using UV light. So you initially have all the switches available. You write it once initially in the lab, and then after that, you will, if you wanted to erase the information, you have to use a specific equipment that can flash UV light onto it, and then the data set can be removed. And then you can write in the next data set again. Again, this writing process is not something that can be done by the customer in the field. It requires specific equipment and is typically done in lab environment. Right? So you have seen masked ROM, programmable ROM, erasable ROM. What do you think should be the next one? Right? Now the erasing is happening with UV light. You would like it if it can be done electrically. So that is the next topology where you have electrically erasable, programmable, read-only memory. This is also called as E-square ROM. And then finally you have the flash ROM. So a flash ROM can be thought of as a version of EEPROM, wherein you have additional circuitry that will allow you to selectively erase and write contents into the flash ROM. Okay, so there are different types of prompts, and typically you are likely to work with if you are working, this might be of the most interest to you, because the equipment needed to read and write into it, reading is very easy, of course. The equipment needed to erase the content and write into it is going to be much simpler if you use an EEPROM or a flash prompt. Okay, so now in our first lecture I told you that if you had to implement a digital circuit, you can potentially do that by taking individual AND gate ICs, NOT gate ICs, NOR gate ICs, etc., and assembling on a breadboard. Another way would be to use devices like a ROM to design your combinational circuit. Can you tell me how you think this is going to be possible? Okay. So any Boolean circuit you take, any Boolean expression you take, this can be represented in a sum of products form, right? What do you need to implement something in SOP form? You need to take the product, then you need to be able to take the sum. So taking a product means what sort of gate are you looking at? AND gate. And if you are taking the sum, what do you need? You need an OR gate. Now already we have seen that our read-only memory has the functionality of the OR gate, right? So only thing I need to check now is if this decoder is somehow giving me an AND gate functionality, right? So can you quickly tell me, what does the function at this point look like? When does that go high? I can take a simpler decoder. Let's say I look at this 2:4 decoder. When does this pin go high? When I1 and I0 are 0, right? Otherwise it is 0. So is it then right for me to say that this is implementing I1 dash into I0 dash, right? Similarly, this is I1 dash into I0, this is I1 into I0 dash, and then this is I1 into I0. So given two inputs, I have calculated all possible min terms, all possible product terms for those two inputs, right? Now, if I were to put an OR gate, right, and then let's say I make the connection here and I make some connections like this, and I'm going to call this as my function F1, this as my function F2. Can you tell me what is F1? F1 will go high when either this line goes high, this line goes high, or if this line goes high. So I can write F1 to be I1 bar I0 bar plus I1 bar I0 plus I1 I0. Okay. Similarly, my F2 is simply going to be I1 into I0 bar. So now I have used a read-only memory to implement a Boolean function which was in a SOP format, right? So if you had a large Boolean function that needed to be implemented, you can potentially buy individual AND gates, OR gates and then implement it, or you can purchase a single read-only memory, right? Code in the type of truth table you want inside and you have your result. So let me give you an example problem to work with. So let's say you have to design a combinational circuit using a read-only memory. This has 3-bit input. The output is the square of the input. Right? So why don't you give it a try? So how many bits do you need at the output? You need 6 bits. So I assume that you can fill in this table. Now, after you have filled this table, right? What is the first thing that you notice? What comment can you make about B0? Is that same as A0? You'll get your B0 to be same as A0. Right? Which means you don't need to store this information anywhere. Whenever A0 comes, you directly connect it to B0. What about your B1? It is 0 at all times. Right? So this also you need not use a combinational circuit to implement. Directly connect your B1 input to 0 at all times. B1 output to 0. So that means we need to save B5, B4 and B3. So B5, B4, B3, B2 in a read-only memory. Right? So now to implement this, so I have A2, A1, A3, sorry. I have A2, A1, A0 coming in. I need my outputs to be B0, B1, B2, B3, B4 and B5. So I will feed B0 directly. B1 is 0 at all times. Then I can simply use a read-only memory whose outputs are given by B2, B3, B4 and finally B5. What is the size of this read-only memory? How many words can this read-only memory store? 8. Right? So this is 2 power 3 cross. How wide is each word? 4. Right? It's not 6. You are not taking B0 and B1 from this read-only memory. So this is only 4. This is 2 cube into 4. And how does the data set in this look like? So now I can have a truth table for the read-only memory. This is also sometimes called as the lookup table. So now I'll have A2, A1, A0 and whatever is the value that you had in the table previously. So B5, B4, B3, B2. So this section of your table is the data that is being stored inside the read-only memory. Is that clear? So for example, if this is all 0, your output is going to be 0. If this was all 1, your output should correspond to this information. So that is 1, 1, 0, 0. And you can fill in the rest. Any questions on this? So what we have done now is that we have now recognized that our read-only memory can be thought of as an AND array of ANDs followed by an array of OR gates. Right? Now, which of them is programmable now? Is the AND gates programmable or is the OR gates programmable? Only the OR gates are programmable, right? Because you can program where you want to put these connections. The AND gates are now determined by the decoder. It is fixed. You are calculating all possible AND gates. Right? You are calculating all possible product terms. Which means if you give I1 and I0 as input, you know that you are going to get 4 minterms at the output corresponding to this. So for the AND gates, there is no programmability. You are calculating all possible minterms, but at the OR gate side, you have some programmability. So your AND gates, this is a fixed array of AND gates, just that it is implemented using a decoder, whereas your OR gate inputs are now programmable. So now this should give you some more ideas, right? If you were a businessman or a businesswoman looking at this, what is the second thought that will come to your mind? So if I were to sell an IC with an array of AND gates and an array of OR gates such that they can implement all forms of SOP, this looks like a nice business idea, right? And we already have read-only memories in the market where it is creating all possible AND gate input combinations and programmable OR gate combinations. What would be the next idea that you will think of? Sorry? Yes, right? So if this is programmable, why can't we make this also programmable? Right? And the next question might be, what if I make this portion programmable and I make this portion fixed? So all of these ideas already exist and they have very specific names to refer to them. So when you use a fixed AND array followed by a programmable OR array, then you are dealing with a read-only memory. So in particular, we would like to deal with a programmable read-only memory so that we can put in the data set that we want. If you make both your AND and the OR array programmable, then it is called as a programmable logic array. If you have your AND gates alone programmable and you use a fixed OR gate array, then it is called as a programmable array logic. Okay. Any guesses on why it is called as PAL and PLA? So, PAL stands for Programmable Array Logic and PLA is Programmable Logic Array. Right? Why do you think this naming convention came up? Actually, no particular reason. So, two separate vendors developed this and brought it to market at the same time. And the vendor who brought in this sort of a structure called it Programmable Array Logic. The vendor who brought in this to the market called it as Programmable Logic Array. So, now we have to deal with this name. Right? So, how I tend to think about it is the most flexible thing here is PLA. Right? Your PAL, your friend, is a little flexible but not that flexible. Right? And read-only memory is very easy to remember because it's a decoder which is all possible minterms followed by a programmable OR. Okay? So now let me show you how a programmable array logic is going to look like. Yeah, first we can deal with a programmable logic array, then I'll show you a programmable array logic. So programmable logic array, the most flexible arrangement, you can see that you have this AND gate, array of AND gates, where the inputs to the AND gates are programmable. You decide whether to short and connect to a particular net or not. Similarly, you have an array of OR gates where the inputs to the OR gates are now programmable. Right? So in this particular architecture, I have also shown that you have an XOR gate at the end. What is the functionality of this XOR gate? Let's say you got some function here, right? This XOR gate is being given an input of 1. So if you had, let's say, some function f0 here, what is the relationship between f0 and f2? It is not it. That's all, right? And if you fed the other input as 0, then the same function is going to come out. This is only to have a programmable inversion at the output. Okay. So given this circuit, can you quickly tell me what is the function f1 and what is the function f2? So we'll worry about this. So this portion, are we inverting the function here? Is there an inversion happening from here to here? No, right? There is no inversion. The other input to the XOR gate is 0. So if this is 1, you will get 1 here. If this is 0, you'll get 0 here. So no inversion is happening from here to here. So now we have to find out what is the function here. That is an OR of 3 terms. So we simply now have to identify what each of those terms are and then add them up, right? So can you tell me what this term is? Right? That depends on this and this. So that is simply A dot B plus, what is the second term? So what is this? A, and what is this? C. So this is AC. Quickly tell me what this is. That will be A bar, B, C bar. Similarly, we can write the function for F2. From here to here, there is an inversion. So I'll directly show that first. Now this is a sum of 2 products. What is this value? That is AC plus, what is this value? That should be equal to BC. Right? So now you have vendors who will sell you this sort of a programmable logic array. This is a very, very simplistic example just to show you how this will work. But in practice, the size of the number of AND gates and the number of OR gates is going to be large. Any questions on this? Which one should be AB bar? This one, is it? This one? Oh, sorry, F1. I'm hearing left one. This should be AB bar. Yes, you are right. Okay. Now let me quickly show you a programmable array logic. Right? That will typically look like this. So this figure has been taken from Morris Mano textbook. So you have inputs I1, I2, I3 and I4. You take the true version and the complemented version of that. So you have I2, I2 bar, I3, I3 bar, etc. So effectively, because this is connected here, this line, the whole line is now I1. And this whole line is now I1 bar. Right? So you have these array of lines that are crisscrossing, and then you decide whether you want to connect them or you want to leave it open. Because this is a programmable array logic, the inputs to the AND gate are programmable, which is why you are able to program things here. But the inputs to the OR gate are fixed. Right? And then finally you can take the output here. So in this particular case, in this particular figure, they are also feeding in the output back to these 2 lines. So that will allow you some more complicated logic array implementations. I'll show you one datasheet figure of a programmable array logic. So this is an actual programmable array logic IC from TI. Right? The IC is called as PL16L8AM, and you can see the complexity associated with it. Right? And then as a customer, you can buy this IC, and then you can decide which of those interconnects are to be shorted and which of those are to be left open. So complicated combinational logic, you can implement it here. Alright, so now again, back to the business idea. If I wanted to implement a combinational circuit, now I can either get a PAL, PLA, or use a read-only memory, right? What is missing? Combinational circuit part, it is done, right? But are digital circuits only limited to combinational circuits? No, right? We want some sort of flip-flops also into this array, right? So with that, we come to other types of programmable logic devices. So in particular, right, so what we would like to see now is a provision to feed our inputs to some sort of AND OR array. So maybe we'll use a PAL or a PLA or a ROM. And then we would like to feed, at least have the provision to feed this into a flop. Most likely an array of flops. And I should also have a provision to feed this back in. Right? And then all of this can be my outputs. Right? This idea also exists already. When you work with such a simple circuit, this is called as either a sequential programmable logic device. Sometimes the S is also used as simple programmable logic device. So just before I conclude the class, all of the devices, all of the systems that we have seen today, including PAL, PLA, ROM, and the sequential PLD, all of these are what we call as programmable logic devices, or in short, PLD. And in next class, we'll see some more complicated programmable logic devices. Thank you.